Welcome to e-lecture online. Today we shall be discussing exclusively on dimensions in physics. Now, dimensions of physical quantities tells how quantity relate to fundamental quantities, mass, length, and time. We have basically two types of quantities. We have what we call the derived quantities, and we have what we call the fundamental or basic quantities. The basic quantities it relates to those quantities that whose dimensions does not depend on other quantities to be derived, while derived quantities are quantities that depends on the fundamental quantity to get their own meaning, that is to get their own unit. So good, let's go back to our board. Now, what are the importance of dimensions? One, dimensions help us to verify the correctness of an equation. Like for example, if we have an equation in physics, F is equals to ma, we know that force is measured in newtons. By the time I analyze the right hand side of the equation, which is mass times acceleration, will I be able to have the same unit? It must balance. So it is only in dimensional analysis it helps us now to check the correctness of an equation. Now, secondly, the dimensions help us to derive the unit of a physical quantities. Basically, most physics students, if you ask them what is the measuring unit of, for example, uh, potential difference, they tend to forget. Like if you ask them what is the measuring unit for velocity, they tend to forget. But in dimensional analysis, it helps us to derive the unit of that physical quantity, whatever quantity it is, it helps us to derive it. So lastly, the dimensions help us to derive the relationship of measured quantities. It helps us to derive the relationship of uh, some measured quantities. For example, if I want to know how mass, force, and acceleration are related to, I can basically derive the formula itself from its basics using dimensions. Now, looking at the board, the three basic quantities that we are going to use basically in dimensional analysis are mass, length, mass, length, and time. Mass, length, and time. So with these three basic quantities, we'll be able to derive the unit of other measured quantities. For example, if a student wants to know the dimension of velocity, what is velocity first? We have to define what velocity is. So from that definition, we'll be able to come up with an expression that will help us to find the dimension. So from the dimension, then we'll now know how the measuring unit right. We know that velocity, from its definition, velocity is equals to displacement all over time. Now, we know that displacement is distance traveled in a stated direction and all over time. So we know that displacement, since it is distance traveled in a stated direction, so distance is measured in what? Is length. It's length that is covered. So, and we know the dimension is capital L. So we can represent it that velocity is equals to length, that is distance traveled in a stated direction, all over time, t. So by indices, I can represent this as L t raised to power minus 1. So you see now that the dimension for velocity, this is the dimension for velocity. And don't forget, recently we said that in dimensions, it helps us to know the unit of every measured quantity. So what is the unit from here? So we know that velocity, the unit will be distance is measured in meters, so it's meters. This is time per second. So you see, this is how we know that every measured physical quantities, we can know the unit from dimensions. So we can go on and on, like in terms of acceleration. Now acceleration, and now we know acceleration is the time rate of change of velocity. So what is the velocity that we have gotten now? The dimension now is going to be, sorry, velocity all over time. Let us go gradually, and already we have gotten that of velocity already. This is the dimension, so it's lt raised power minus 1 all over time t. So by indices, I'll take this t, capital T, up here, and it takes turn of minus 1, so lt raised power minus 1 times t raised to power minus 1. So by indices, I can add these two because they have the same base, and what is multiplicative factor between them, so I'll add the powers. So acceleration is equals to lt raised to minus 2. This is the dimension for acceleration. Then what is the measuring unit for acceleration? L is meters, t is seconds, then square. So you see, this is the unit, that is meters per second squared. Right, next is to find the dimensions of force and what is the measuring unit of force. So from recently we established that mass is measured in, that is the dimension for mass is capital M, and we have gotten the dimension already for acceleration. So we can rightly write it that force, which is F, is equals to mass capital M times acceleration. We got it that acceleration is meters per second squared. Right, meters per second squared. So if we join this, we have that force is equals to capital M L T raised to power minus 2. Now this is the dimension of force. Then what is the measuring unit of force? We know that mass is measured in kilograms, so this capital M represents mass, and mass is measured in kilograms. So F is equals to kilograms. L is distance, but is measured in meters. T is seconds squared. Now, do you see that the measuring unit, we can get it from the dimensions. So now, the measuring unit of force is kilograms meter per second squared. So we can go on and on and on to be able to show that dimensions are very important in order for us to know the correctness of an equation or to derive the unit. So with this, I hope you are able to learn that how to derive the unit of some physical quantities and to know their dimensions. So in the next video, we'll be solving a real valued problem to find the relationship, how physical quantities relate, how equations are being derived. Stay tuned.